Hello everyone, this is lecture 3 of course PE 500. In this lecture, we will deal with first order differential equations and how to solve these differential equations using two common ways. The first is separable functions and the second is integrating factor. So let's start. First order differential equations only involve the first derivative of the dependent variable with respect to the independent variable. So we have the first derivative and we have a function. This function can contain the independent or the dependent variables, which can be a function of x and y. This equation describes systems where the rate of change of a quantity depends on the current state of a specific system. This is an example of a first-order differential equation. We have the first derivative, and we have a function that contains x and y. Once we see that the highest derivative is the first derivative, then this is the first-order differential equation. They are tools in modeling dynamic systems in biology, engineering, physics, and economics. They also provide insights into how quantities evolve over time or space, and that makes them essential for understanding the different processes like growth, decay, diffusion, and oscillations. There are many applications, as we mentioned in the previous lectures, such as population dynamics, where we are modeling a bacterial growth or species interactions, pharmacokinetics, where we are tracking the drug concentration in the bloodstream over time, and chemical kinetics, where we describe the reaction rates in enzyme catalyzed processes. And we mentioned also that we will get a differential equation from a specific system. So at the beginning, you are building a system, or you are making a system, or you have a system, and you need to model it. What is the aim of modeling it in a differential equation is how to solve it. And why we need to solve it? Simply to get the original equation, which will be, for example, a function of t or x, t as time, x as displacement, and based on that function, we can predict the curve or the future points of that process. So now we are at this point. We need to solve a differential equation and know how to solve different differential equations, aiming to get the original equation so we can proceed with getting further points on the curve. So solving a differential equations means finding the function y of x that satisfies the equation, and the solution or the different solutions will provide insights into how systems evolve over time or space, and this will enable predictions and optimizations in bioengineering applications. As noted, we have two key solutions to the first order differential equation. The first is separable equations. A second is integrating factor. Separable equations is a subset of first order differential equation where variables can be separated and integrated independently, and this is a common formula. And we will go further in describing each of them in the following slides. Integrating factors is another method that solves linear first differential equations by transforming them into exact equations, and there is a common formula or the general formula for it. Both techniques are systematic approaches to solve specific types of first-order differential equations, and both of them depend on calculus using integration and differentiation. So let's start by the first technique, separable equations. You can call a function, or you can call a first-order differential equation separable if you can write it on this form. dy by dx, which is the first derivative, equals to the multiplication of two separate functions. The first is a function of x, the second is a function of y. This means that the right-hand side here can be factored into a product of two functions. The first is depending on x, the second is depending on y. Why they are important? Because they are simple and they can solve differential equations analytically. And there are many problems, including real-world problems, that can be solved and modeled using separable equations, such as growth rate, mixing problems, motion under resistance, and decay problems. So how to solve the separable equations? First, separate variables by rewriting the equation so that all terms involving y and dy are on one side, let's assume the left side, and all other terms involving x and dx are on the other. So if we have a function like that, simply we have dy, dx, x, and y. Let's try to separate them. We can simply move y to the left side and move dx to the right side to be rewritten like that. Y multiplied by dy, x multiplied by dx. So in this case, there's a separable differential equation. But if you find something like that, dy by dx plus 2y equals the exponential of negative x. If you try to separate them, you'll not be able to do that. So in this case, this differential equation isn't separable, and we cannot solve it using this way. After separating the variables, the next step is to integrate both sides with respect to its respective variable. So you will integrate this part with respect to dy and integrate this part with respect to dx. After that, if possible, solve explicitly for y as a function of x, so you aim to get y, for example, in the left side, and the right side will be for x, or the equation of x. Let's try to apply that using this example. We have dy by dx equals 6y squared multiplied by x. And when you find something like that, then this means we have an initial condition. And this initial condition will help us to find the value of the constant if it exists. As we mentioned, we need to separate the variables. So we can move y squared to this side and move dx to this side. So we will get dy divided by y squared equals 6 multiplied by x dot dx. Now we can integrate both sides with the respective variable. So we'll integrate this part here with respect to dy. So the integration of this will be the integration of y to the power of -2, because we moved y squared to the numerator with a negative sign. Simply, this is a power. So we will increment here by 1 and divide by -1. So we will get -1 multiplied by y to the power of -1. And this means -1 over y. The right side, 6x dot dx, we will integrate this with respect to dx. In this case, we will get x with a raised power divided by z power. So the result will be 6x squared divided by 2 plus the constant. And why we didn't add a constant here? Simply, we need one constant in the equation. If you added a constant here, let's assume c bar. So you will move all constant together and replace them with another variable called c double bar. So for the whole equation, we need one single constant. Now combine both of them together, move this to the left side, move the result to the right side. Now this is the equation. Next, we need to solve for y. So we need an equation that looks like y equals to something. This equation, simply move y here and move this equation here. So it will be y equals to -1 divided by 3x squared plus c. Now, this is an equation of y. We have an initial condition to find the value of the constant. Substitute. So y of 1, replace every x with 1. So we'll get 1 divided by 3 multiplied by 1 square plus c. So we'll get, and we have a negative here. So we'll get -1 divided by 3 plus c. And this equals to 125. Try to find the value of c. Simply swap between both of them. So 3 plus c equals to -1 divided by 125. Move 3 to the other side. So c equals to -1 divided by 125 minus 3. And this will equal to that result. Substitute with the constant into the original equation. So this will be the final solution of your. So now simply, if you need to do something about this equation, simply you can plot it by substituting with different x values and try to plot that function. And based on the behavior of the function and the shape of it, you can do further processing, such as increasing a substance or decreasing another substance if you are dealing with drug concentration, so you can reach your target of your model. This is another equation. We have dy by dx equals to y over x, and we have also an initial condition here. First step, separate the variables and simply move y here, move dx here, and this will be dy over y equal to dx over x. Integrate both sides, so the integration of the left side will be ln y. The integration of 1 over y equals to ln y. And don't try to say that we can make what we did in the previous example, 1 over y equals to y negative 1. So you can say we can integrate that by incrementing. This will be like that. And this is a mistake because you are dividing by 0. However, as mentioned in the first lecture, you can use a table of calculus, integration or differentiation, to find the direct integrations or differentiations for the different simple equations. If you go to this table, you will find that the integration of 1 over y will equals to ln y. Let's do that on the right side. The same here. The integration of 1 over x will be ln x plus c, and we need a single constant, whether you put it here or here, but it's recommended to put it on the side of x. So the equation would be ln y equals to ln x plus c. Next, we need to solve for y. We have an equation, and before knowing how to solve it, let's first understand this rule. If you have the exponential of ln of something, let's assume it's x, the exponential will cancel the ln and the result will be this thing. The same if you have ln of e over x, this will cancel each other and the result will be this thing. So simply to get rid of ln, apply the exponential to it. So simply raise each side to the exponential, so it will be like that, exponential of ln of y, and the right side will be the exponential of ln of x plus c. This will cancel each other, so you'll get here y. And there is another rule. If you have exponential of a plus b, this will equal to the exponential of a multiplied to the exponential of b. And if you have the exponential of a minus b, this will be the exponential of a divided by the exponential of b. So for the exponential, the plus is converted to multiplication and subtraction is converted to division. So here we have plus, it will be converted to multiplication. So this will cancel each other. So we'll get x multiplied to e over c. As we mentioned, we need a single constant, so we can replace this one by c1. So the final equation can be y equals to c1 multiplied by x. We have an initial condition, substitute with that initial condition, so x will be 2 and the result will equal 4, so c1 will be 4 divided by 2 will be 2. So the final solution as this initial condition will be y equals to 2 multiplied by x. The second technique is called integrating factor. And integrating factor is a function used to solve first differential equation on this form. You have the first order plus a function of x multiplied by y equals to a function of x or another function of x. And integrating factor, which is denoted by mu of x, transforms the left-hand side of the equation into an exact derivative, making it easier to integrate. So why do we need to use integrating factors? Simply because some equations, which are first order, cannot be solved directly by the separation of variables. And this way, or this technique, rewrites the equation into a solvable form by following a systematic way. So how to solve it? Simply identify the variables p of x and q of x. P of x will be the one that's attached to y, and q of x will be the one which is free, without any y. After that, compute the factor, which is the integrating factor, mu of x, equals to e, or the exponential of the integration of p of x with respect to dx. After that, multiply the entire equation by the integrating factor to make the left-hand side a perfect derivative. Simply apply the derivation of this equation, which is mu of x multiplied by y, and here mu of x multiplied by q of x. Then integrate both sides to solve for y, and lastly solve the entire equation for y. So the trick here is to extract an integrating factor and multiply it to both sides to convert the equation into an exact equation. And in this way, it will be easily to solve it. Let's apply that with an equation. If you remember this example, it was not separable when we dealt with the separation because we cannot separate dy and dx individually. Now in this equation, we have an initial condition y of 0 equals 1. So the first step is to identify p of x and q of x. And in this case, as mentioned, p of x will be the one attached to y, which will be 2, and the q of x will be the other one, which will be the exponential of negative x. Compute the integrating factor, which is mu of x, by simply apply exponential of the integration of dx. So the exponential of the integration of 2 with respect to dx will be, let's take this one, it will be 2x, and let's ignore the constant for a while. So replace that one with 2x, so the result will be e over 2x. Use this integrating factor and substitute in this equation. Mu of x was exponential of 2x, put it here, y put it here, mu of x exponential of 2x, and the q of x was exponential of negative x. As noted, if you have exponential of a plus b, this will equal e of a multiplied by the exponential of b. So in this case, we have the right side, so you can convert it to the left side for easier manipulation. And this is because we have here 2x and here negative x. So simply we can combine both of them together to get a single variable, which will be exponential of x. Keep the left-hand side as it is. Now integrate both sides. The integration will cancel the derivation. So the result of the left side will be the exponential of 2x multiplied by y. And the integration of the exponential of x will be the same, because if you apply derivation or integration of ex, the result will be the same. So it will be e over x. And let's put the constant. Substitute by the constant. Replace every x with 0 here and here, and every y with 1 here. So simply the constant will equal 0. So the equation will be exponential of 2x multiplied by y equals the exponential of x. Now we need to solve for y. As mentioned, we need y equals to something. So simply divide by the exponential of 2x. It will be y equal exponential of x over the exponential of 2x. And this will result in the exponential of negative x. So the final solution will be y equal to the exponential of negative x. A second example, the first derivative, negative 1 over x multiplied by y equal x squared, and we have initial condition here. So as mentioned, the first step to identify the variables. So this will be p of x, this will be q of x as here. Compute the integrating factor, simply take p of x, put it here and apply integration. So the integration of this part will be negative ln of x. As mentioned, the integration of 1 over x will be ln x. So it will be exponential of negative ln of x. If you encounter something like that, exponential of negative ln of something, there is a rule that says you can move the negative as a power to the thing. So move the negative as a power here. It would be the exponential of ln of x raised to the power of negative 1. And why we did that? So we can benefit from cancelling the exponential and the ln together. So the result will be x raised to the power of negative 1, which is 1 over x. We have the integrating factor. Now we can substitute and multiply by that integrating factor. 1 over x multiplied by y, 1 over x multiplied by q of x, which is x squared, which is here. Both of them will result in x. Apply the integration for both sides here. This will cancel each other. So we will get 1 over x multiplied by y here. And the integration of x will be x squared over 2. And we have a constant. Solve for y. So we have a substitution or initial condition. Substitute by x by 1 and y by 2. So it will result in a constant will equal to with a value of 1.5. Substitute with that constant here. we will get 1 over x multiplied by y equal to x squared over y plus 1.5. We need to solve for y to be something, so we need to get rid of this. So you can simply multiply both sides by x. So it will be y equal to x multiplied by the rest of the equation. X multiplied by x squared, it will be x cubic multiplied by half, which is here. 1.5 multiplied by x will be here. So the final equation will be y equals to 0.5 x cubic plus 1.5x. Now let's move from traditional examples to applications. Let's start by the logistic growth model. And this model describes a population growth that slows as the population approaches its carrying capacity, reflecting resource limitations. We have dealt with that model previously in an earlier lecture, and we here in this lecture will try to find the population equation with respect to the time. So we need to find at the end P of t as an equation. We have the model as a first order differential equation, as you see here. We have r as a constant, t multiplied by 1 minus p over k, where the p is a population size at time t, r intrinsic growth rate, and k is the carrying capacity. We need first to determine which approach should we follow, whether it's separable or integrating factor. As you see, k, r are constants, and p is found without any time factors or variables. So simply we can swap between dt and this equation. So we can use the separable technique to solve it. So first, separate the variables. So we will get dt in this side, and we will move that part in this side. As you see here, dp over this factor equal to r dt. To be able to solve this part, we need to apply partial fraction, because we will gain here b squared. So it's better to apply partial fraction to make it simpler, so we can apply integration after that. So how to apply partial fraction? We need to apply partial fraction only to this. So this will be divided into two parts, one that contains p and another that contains 1 minus p over k. So it will equal a over p plus p over 1 minus p over k. We now need to find the variables a and p. So simply construct back a single equation by multiplying a by 1 minus p over k plus p multiplied by p equals to 1. Now we have an equation. Try to find the values of a and p. Simply this can be converted into a minus ap over k plus pp equals to 1. Find the factors or coefficients of p power of 0 or p power of 1. So p power of 0, this means that the variable isn't multiplied by p, and p to the power of 1, this means it's multiplied by p to the power of 1. So simply the coefficients of p to the power of 0 is a, nothing here, and 1. So a will equal 1. P to the power of 1 will be that part, and there is nothing here, so it will be 0. So the factor a over k plus p will equal to 0, and there is a negative here. So substitute here by 1, so p will equal to 1 over k. Now we have the value of a and p. Substitute in the equation, it will be like that. Next, we need to integrate both sides. So get the left hand side and integrate it. So simply the integration will be split because there is a plus here. So it will be the integration of the first part plus the integration of the second part. And here is the right hand side. The integration of this part will be ln b, and the integration of this part is also simple. It will be ln of the numerator divided by the factor of p. So simply it will be ln of 1 minus p over k, and it will be divided or multiplied by 1 over k, like that, and there is a negative sign here. All of that is multiplied by the factor 1 over k, so this will cancel each other. The integration of r dt will be rt plus the constant. Simplify, ln b will be here. This canceled each other. There is a negative sign here. Ln 1 minus p over k equal to rt plus c. If you find ln of a minus ln of p, this simply can be converted ln A over B. And ln A plus ln B can be converted into ln AP. So simply this will be converted to that, B over this factor. Next step is to solve for y. So simply when you find ln, you can apply the exponential. And this because the exponential will cancel the ln. So exponential for both sides. So it's exponential over the left hand side, exponential of the right hand side. This will cancel each other, will result in p over 1 minus p over k. And because there is a plus here, it will be converted to multiplication, because we mentioned e over a plus p will be converted e exponential of a multiplied by exponential of b. The same ea minus p will be exponential of a divided by the exponential of b. As you notice, the rules here are the opposite. Now it will be exponential of rt multiplied by the exponential of c. So simply convert this to another constant, let it c1. So we now have an equation. We need to simplify this equation so we can get p on a side and the rest on another side. So simply move the numerator to the other side. It will be like that. Spread the multiplication. It will be ERT multiplied by C1 multiplied by 1, like here, minus P over K multiplied by the same. Now we have two sides that contains P. Collect them together by moving this part to the left hand side. It will be P plus P over K multiplied by this factor equal to this factor. Factor out P. It will be 1 plus 1 over K multiplied by the exponential of RT multiplied by C1 and the right hand side. Now we can get P simply by moving this from multiplication into division here to be like that. So now we need to find the constant C1. So let's assume at time t equals to 0, the initial population was P naught. So simply substitute by t here in the equation by 0. So the exponential of 0 will be 1 here. The exponential of 0 will be 1 here. And all of that will equal to P naught. Now we have this equation and we need to find the value of C1. Simply take this part to the other side by multiplication, like here. Spread the multiplication, P naught multiplied by 1, P naught multiplied by C1 over K, like here and here C1. Move C1 to the other side, so it will be P naught will equal to C1 minus P naught over K multiplied by C1. Factor out C1, it will be P naught equal to C1 multiplied by 1 minus P naught over K. 1 will be K over K, so it will be K minus P naught over K, like here. Now you can move this part from here into here, so it will be C1 will equal P naught multiplied by the swapping between numerator and denominator, because we are simply, as we noted, we are moving K minus P naught over K from the right side to the left side, so it will be the same as multiplication but swap between the numerator and denominator. Now we have C1. Using C1, substitute in the equation. So substitute here, it will be like that and like that. So simplify this equation. It will be exponential of RT multiplied by B naught multiplied by K over this factor. And here will be 1 plus, this will cancel each other, exponential of RT multiplied by P naught divided by this factor, like here. Simply multiply the numerator and denominator by this factor. So it will be exponential of RT multiplied by P naught multiplied by K, and 1 multiplied by the factor, it will be K minus P naught. This will be cancelled, so it will be plus exponential of RT multiplied by P naught. Now we have this equation. To make it simpler, simply divide by the exponential multiplied by P naught, so this will be cancelled and will remain K. This will be divided by this factor, like here, and this will be divided by this factor. This will cancel each other and will remain the exponential of RT with a negative sign, like here, and this will be divided by that, will get 1. Now we have this equation. Exponential of RT in the denominator can be moved to the numerator with a negative sign, like what we did here and here. Factor out the exponential, so the exponential will be here. The factor will be k over p naught minus 1, like here, and plus 1 will be here. Move 1 to the front, so it will be k over 1 plus this factor. 1 is p naught over p naught, so it will be k minus p naught over p naught, like here. So the final equation or expression will be k over 1 plus exponential multiplied by a constant. And that's why it's called a logistic model, because a logistic model follows equation of something or a constant over 1 plus the exponential of something, and it can include also a constant here. So this equation on this format. Now we made the derivation, we can plot it easily or using a software, and we can get the curve or of the population growth. Let's move to the next application, drug concentration in the bloodstream. And this model describes how drugs are absorbed, distributed, metabolized, and eliminated from the bloodstream over time. There is an exponential decay model here, which is a first order differential equation. dc by dt equals to negative kc, and k here is the elimination rate constant, and c of t is the drug concentration at time t. We need to solve it, so simply we can use separable by simply moving c to this part and moving dt to this part. So it will be dc over c equals to negative k dt. So integrate both sides. So the integration of 1 over c, it will be ln c. The integration of this will be negative kt plus c naught. And we use c naught because we don't need to use c because we have another c here. So to differentiate between the concentration and the constant, we put here a constant c naught. Now we have an equation. To get rid of the ln, simply apply exponential to both sides. So it will be the exponential of the left side equal to the exponential of the right side. This will cancel each other. So we have c equal to the exponential of negative kt multiplied by the exponential of c naught. Again, plus or addition in the exponential will be converted into multiplication. Convert this to another constant, let it c1. So we have this equation. So the final solution will be c of t equal to the exponential of negative kt multiplied by a constant c1. Again, we can plot this and find the drug concentration of a specific material or a specific medicine and find when this concentration decays in the bloodstream. And to do that, we can use MATLAB or Python to plot it and also solve the different differential equation of the first order. So simply let's start by a simple equation and then move to the applications. We need to solve this equation or the first order differential equation and validate our results with MATLAB and Python. So we have an equation, we have initial condition, start to apply separable variables because we can separate x and y together like what we did here. Apply the integration, it will be ln, and this will be x squared over 2 plus c. Again, apply the exponential to get rid of ln and to get y. So simply the equation will be like that. Convert the exponential of c to another constant. So the final equation will be y equal to exponential of x squared over 2 all multiplied by a constant c1. We have initial condition, substitute to get c1. c1 in this case will equal 0. So the final solution will be y equal to exponential of x squared over 2. Now we need to validate this result with MATLAB and Python, given this equation and this initial condition. So you'll find the scripts under the name Lecture 3, Lab Exercise 1, Separable, for both folders, MATLAB and Python. In this example, let's start with Python. First, we imported the necessary libraries, including NumPy for mathematical operations, SciPy to use the function solve initial value problem, and this is a built-in function that solves initial value problems using numerical approaches, and we will do that later in the lectures. But we will use this to compare between the analytical solution and the numerical solution to find both are the same. We use plot for plotting, as we need to plot at the end, and we use SymPy, multiple built-in functions or classes from here. First, you need to define the separable equation as a function, and this will be used later for the numerical approach in the solve initial value problem using this function. So define here the problem. So the problem is x multiplied by y, and we have an initial condition y of naught equals 1, and also we have x naught equals 0. Next, define the symbols as we did in the first lecture, and these symbols will be used using the SymPy to solve the equation and find the original equation from the derivative one. We have x, we have y, we have a constant, and y is a function of x. We need to define the separable function dy by dx minus xy, and we will use the function dsolve from the SymPy library and solve it analytically with respect to y. This will gain the analytical solution. We did that, so the function dsolve here is a function that solves the separable equation analytically, but you need to give it the separable equation as constants, and you need to define solve it with respect to what, and here we defined y. We need to get a specific equation based on the initial condition x naught and y naught. So substitute for each y by the value y naught, and then solve the equation to get the constant. Simply get the right hand side, substitute by x of the value x naught, subtract by y naught, and we aim to find the constant c1. Now we have a constant value. Use that constant value and substitute back in the solution to get the specific solution. Now we have the specific solution here. So we have general solution, constant, and specific solution. From the three of them, we can validate our solution simply like here. The general solution is left hand side, which is here, right hand side, which is here. C1 equals 1. So let's back here. This should be multiplication, and this should be multiplication. So the value of C1 will equal 1. So we can get this equation. So this is a typo here. We got a constant C1 here and C1 here. Now we can validate the result. Now the specific solution is exponential of x squared over 2 like here. So this solution and this solution using hand calculation and Python, both are the same. Now we need to plot the results of the analytical solution and the numerical solution. We know that we can retrieve the analytical solution, and later we will know how to derive to get the numerical solution. But for now, let's validate both of them together. Create x-axis and substitute for the right hand side in the analytical solution for each point in x. We have x and y that will be used to plot the analytical solution. Let's get the numerical solution. Using the solve initial value problem, define the function to solve, define the interval of integration. Let's assume from 0 to 2, and you can increment that interval. Define the initial condition and define the x-axis. You can simply define it here or use this variable because both are the same. Now get the x of the solution by getting dot t, and get the y-axis by getting y of naught. Plot it as red and circles, add a label, and set the marker size of 4. Then plot the analytical solution with a color blue and line width of 1.5. Set labels, set title, set the legend, and the legend here will get the benefit of the set labels here and here. Set a grid. You can save and show the figure. After displaying it, you will see the red circles for the numerical solution and the line in blue for the analytical one, and both matches each other. Now let's move to MATLAB. Define the symbols using sims, define the initial condition, define the separable equation dy by dx equal to x multiplied by y. Use the function dsolve to solve this equation. Now we have general equation. Substitute by x of x naught equals to y naught. This will get the initial condition. Use the initial condition with the constant c1 to get the value of it. using the solve function. We have the constant value. By substituting with the constant value to replace C1, we now have a specific solution. Now we have general equation or solution. We have a constant. We have a specific solution. You can compare your results again. C multiplied by the exponential x raised to the power of 2 divided by 2. And here is the specific solution when C1 equals 1. We need to plot it. Again, we defined x-axis, substituted to get y-axis. We defined the function to solve it numerically using a function in MATLAB called ODE, ordinary differential equation 45. Plot the numerical solution as circles in red with a marker size of 4, and for the analytical solution in blue, set labels, set the legend, and the legend will get the name from here and here. You can save the figure and display it, and this is the result. This is the legend, this is the analytical solution, this is the numerical solution, and both matches each other. And this figure matches this figure. From at 0, it's 1, at 2, it's above 7. Now let's move applications and apply MATLAB and Python on them. Let's start again by the logistic growth model. We got this equation as we derived it earlier in this lecture. We have initial conditions, and we need to apply MATLAB and Python to get the analytical general solution and specific solution. Simply, if you substituted with these factors or constants in this equation, you will gain k, which is 100, 1 plus r equals to 0.5, so e, the exponential of t over 2. This is multiplied by this constant, and this constant will be k, which is 100 minus 10, which is 90, over p naught, which is 10, will equal to 9. So this factor will be 9. So the equation will be 100 over 1 plus the exponential of negative t over 2, and all multiplied by 9. So here we will use the same code, but we will define the defined model or the defined function, the initial conditions, and the symbolic equation. So simply, we imported the same packages, NumPy, SciPy, Matplotlib, and SymPy. We updated the model to be logistic growth. It will be RP multiplied by 1 minus P over K. We defined the initial values or the constants. We define the symbols T, P, and the constant, and B is a function of T. We define the logistic equation P dB by dt minus RP multiplied by 1 minus P over K. We used again the dsolve function to get the general solution, substitute it, and use the solve function to get the constant value as we did in the first code. Again, after getting the constant value, we substituted back to replace the constant with that constant value to get the specific solution. Now we have the general solution, constant, and specific solution. And now we can compare this with what we retrieved. Simply, the constant here is negative because in the general solution, they added negative in the numerator, negative in the denominator. So simply, all of them will cancel each other. So the constant is 9. So the specific solution will be 100 because this will cancel this and cancel this over 1 plus 9 multiplied the exponential of negative t over 2. So both are the same. Now we need to plot and gain this figure. Again, define x-axis, substitute for each x point to get the y point, use a solve initial value problem, and define the conditions. Now we have arguments r and k as constants, and don't forget to include them in the parameters here. If you notice here, we have x only and y in the first code, so we added here only x and y, but in the second code, we have or, which is time, p, r, and k. You can define them whether you use them or not. Then you can plot the numerical solution, analytical solution, and the rest are the same. Define x and y labels, title, legend, grid, and you can save and show the figure. And this is the output. Again, the numerical solution in red circles and the analytical solution in a line colored in blue. We will do the same using MATLAB. We define the symbols, constants, the initial condition. We define the logistic model, used the dsolve function, got the general solution, substitute it to get the constant, use the constant to get the analytical solution. This is similar to what we did in the first code in MATLAB also. Created x-axis, substitute to get the corresponding y points, use the ODE 45 to solve it numerically, plotted it, and defined the parameters for labels, titles, legend, and finally saved and displayed the figure. And this would be the corresponding plot. At 0, it's 10. At 20, it's around 100. And for Python, it's the same. At 0, it's 10. At 20, it's around 100. The last example is to apply the drug concentration dynamics model using Python and MATLAB. And here we got this equation and we defined the parameters or the initial values. K equals to 0.5. So the equation will be C equals 10. So it will be 10 multiplied by E, the exponential of negative K over 2. So this will be the equation. We will use the same script, but we will update the equation, constants, and symbols. We will use the same code in Python and MATLAB, but update the model, the initial values or constants, the symbols, and the symbolic equation. We will use the same law, get the general solution using the dsolve, using the solve to get the constant value, substitute to get the specific solution, create x and y axes, using solve IVP to get the numerical output, plot both of them together and update the legends and labels accordingly, and you can save and display the figure at the end. And this would be the output. Once the time increases, the drug concentration decays and decreases over time until it reaches 0. So you can simply, at time t equals around 10, the concentration in the blood equals to 0. So by plotting that model, you can understand the effect of your model or the effect of the drug concentration in the patient bloodstream. And at a certain point, you can intervene and say at time equals to 0.5, which will be a concentration of 1, I can intervene and do something here. Let's check the output. So C multiplied by the exponential of negative t over 2. The constant is 10. By substituting, this will be similar to what we retrieved. For MATLAB, we will again use the same code, but it changes symbols, parameters, initial condition, the symbolic equation, and follow the same pattern as we did in the previous two scripts for MATLAB to get the general and specific solutions alongside the constant, and also use the ODE 45 to get the numerical solution and plot until you reach to save and display the figure. This will display the corresponding figure. At time 0, it's 10. At time around 20 or around 10, it's 0, as you see here also in Python. So both solutions result in the same figure and same output. You can also check that and validate that the output is 10 multiplied by the exponential of negative t over 2. So there is a typo here. This will be t, not k. So in this lecture, we have learned two techniques to solve first order differential equation. The first is separable, and we knew the steps of it, and the other is integrating factors, and we also knew the steps of it. We moved to solve multiple examples and real-world applications, including drug concentration and growth model. Then we switched the gears to move into handling these mathematical models using Python and MATLAB, and we validated the output of these scripts with what we did during the lecture. We also knew how to script MATLAB and Python so we can write a differential equation and the corresponding constants and initial values and get the output. And also we knew how to plot the numerical solution and the analytical solution, and we showed that both of them matches together. We dealt with the analytical solution and provided the numerical solution to validate the analytical one, but in a later lecture we will understand how to handle the numerical solutions using hand calculations.